Okay, today we're starting a new unit. We've got some minerals to talk about here in the first couple pages. There's a page or two on volcanoes, and then we get into the rocks and the rock cycle. So we're starting off with minerals because minerals are kind of the thing that make up rocks for the most part. So we take a look at a very classic mineral. We've got this yellow one here called sulfur. It's made up of literally one element, only one chemical, only one thing. Whereas if we take a look at something like this one wasn't apparently Arcos, I would have called it granite had I picked it up. But if you take a look at this one, you can see that there's a bunch of different little specks or crystals in this one. Each crystal, each kind of color in here is a different mineral. So any of these ones that kind of look pink would more than likely be feldspar. This one right here. Any pink and like granite is feldspar. If it's one of these white shiny ones, probably quartz. If it's black, it might be I don't know, gneiss. That's an actual rock, like magnetites or hematites or any of the ones that are a little bit darker. Gabbro. Okay. So minerals are the building blocks of rocks. If we think back to one of our first units this year, we could think of a mineral sort of similar to an element, where an element made up molecules. Well, minerals make up rocks. Sorry. So, four characteristics of minerals. So, kind of how we know if something is a mineral or not. First of all, it's solid. It has a crystal shape or a 3D structure to it. Not all of them are easy to see in their natural state. Some of these crystal shapes come from like breaking the mineral and seeing what shape forms then. But on this one, this is actually what an Illinois city is named after. It used to be the largest city in Illinois back in the day because of this mineral. This is galena. It is a ore of lead, and why galena is named the way it is, why galena used to be a very, very rich place and populous place because they mined galena there. So that one had a square shape to it. It's inorganic, so it doesn't have carbon or hydrogen in it. Some minerals do have carbon, but they do not have hydrogen, meaning diamond is a mineral. It's made out of carbon. I don't have one of those here, but I did have graphite. So stuff that you can write on paper with. I don't know if it'll write as well as some of the other forms that I have, but really, this does not look exactly like the other kind of wrote. Doesn't look exactly like the mineral I used to have of graphite. It's not quite as shiny and easy to write with, but it does have some parts that look a little bit like it. And they're not man-made. So I guess diamonds that are made in a laboratory technically don't fit the bill, but natural diamonds do. Okay. Oh, the next stuff I had over here, I had a comparison of two different substances to figure out if they are a crystal or not. So there's one called halite, which I don't remember seeing on here actually, which is weird. I wonder if I've got another one. That's rock salt. It is solid. If I had it here, I could show you the square part. Maybe I'll find it later. But it has a square shape to it. If you take out salt crystals in your house, like salt you put on your food, and you look at them really close, you'll see that they're little tiny cubes. It's got a composition of NaCl, so it doesn't have carbon, it doesn't have hydrogen. And it forms from old oceans, so it's made naturally. You don't make it in a lab or anything like that. It's made from evaporation of water. So this is a crystal, this is a solid, this is one thing, this is not man-made, it is a mineral. If we look at ice, it is solid. The crystal does have many shapes, but it does form crystals. It's made out of H2O. It does have hydrogen, but it doesn't have carbon, so it's not organic. And it forms when water freezes. So technically, ice is a mineral as well. It's weird to think about. We don't usually think of it as a mineral. It doesn't last that long if it gets warm enough, so then it becomes a liquid, and it's not a mineral anymore. But that does fit the bill that it is a mineral too. I used to do this with my 8th grade class mainly because they hadn't seen any of these chemical symbols before. So let's just briefly go over an element, a compound, and what we're looking at here, even though you should hopefully know that from earlier this year. So an element is a specific type of atom with a certain number of protons. Um, Sulfur has 16, I believe, because it's atomic number 16. Carbon has 6 protons because it's atomic number 6. Okay. Compounds is when you start mashing and bonding and joining 2 or more atoms. And that was because they wanted to be stable. So if we take a look at some of these down here, this is an actual mineral here. Hematite or magnetite can have this same chemical formula. 2 irons, 3 oxygens. Or we might have potassium phosphate, so 3 potassiums, 1 phosphorus, and 4 oxygens. And that's pretty much all I need you to know. I don't think we're going to do much with this. Really, the main point of doing this was so when we get to this mineral ID sheet, these compositions don't freak you out and make you go, what the heck are those? Okay, so like graphite is just a carbon. Galena that we saw earlier is lead sulfide, PBS. Magnetite is Fe3O4, that kind of thing. So it's just trying to get you used to not freaking out when you see these compositions. Otherwise, not going to be too concerned about most of the notes that are on this bottom section here. Okay. What I will be concerned about is the stuff on minerals that was up above and also some of these properties of minerals. So some of the properties, you can describe the way the crystal appears. So you can say what color it is. It's not generally the best way to ID a mineral is only its color. And if we get to some other minerals, which one is this? It's fluorite. Where's my quartz? Quartz. Okay, this one is quartz, but quartz can be clear, completely clear. This one is more kind of a cloudy white. It can be purple if it's an amethyst. It can be got a pink shade to it. It can have lots of different trace minerals in it or trace elements in it that give it a certain color. So not the best way to ID by because a lot of different minerals can have a bunch of different colors. It is maybe useful to eliminate certain options or just to make yourself more confident. But usually you want to use a combination of all these things, not just color and the way it appears visually. So luster, how light bounces off of a mineral. There are a bunch of different fancy names for specific lusters, but for our purposes, there's really only a couple. It can have a metallic luster, which the best one I have here for that is galena. It's very metallic and shiny, I guess. It's going to look like a metal. Versus something that doesn't have a metallic luster, like if I find feldspar, It's overall dull and looks kind of earthy. Okay, but there's all sorts of different descriptions for the non-metallic luster. There's like vitreous, which looks glassy. There's I don't know, even some of the other names. I wonder if there's some of them on here. Nope, this one doesn't list the luster. Okay. So really, I just need you to know metallic and non-metallic. You can even see that over on this side. That's how this one's separated. Metallic luster, non-metallic. There's one that's either or. Right. Streak. Streak refers to what color the powdered mineral looks like. So how you usually do that is you have a little porcelain plate, just a little piece of pottery essentially, and you take the mineral, and if it's softer than this porcelain, you can streak it on there. And it's hard to see that, but this one is obviously yellow. I took a piece of sulfur and streaked it on there. If I take another one, this one I think is magnetite, and I streak it, you see that it leaves a streak on there, which this one is black. Nothing surprising there. There is one mineral in here, supposedly, according to the box, that is worth streak. Oh, it's a completely different color than I have ever seen it. That's why I couldn't find it. This one is one of the most common iron ores. It looks kind of orange and rusty right now because it literally is metal or iron oxide, which is rust, Fe2O3. My other box of minerals that I used at my other school, this was black. It looked like magnetite. It was this color instead of red. So that was my search image, which is why I couldn't find it. And when it looked black and you did the streak was still red. So that was one of the useful things for identifying that mineral, is because it looked black but had a red streak. So this one is a little different. It looks red, looks rusty, without having to streak it. Okay, so that's what the streak is. You can figure out what colors those are. The crystal shape. I don't really have the best, other than that galena that I showed you earlier, which has this kind of cube shape to it. That was my best one. There's calcite that I used to have, which is in here somewhere. This one has got not a cube shape. This one you can kind of see it. It's a kind of 3D rhombus. It's kind of at an angle. That's its crystal shape. Those are some of the best examples. And then hardness. They measure it with something called the Mohs hardness scale. Mohs was the dude that first described this. So you take something that's soft like talc. If talc was in here. 20. Okay, it is. Take something soft like talc, which is this hardness of 1. You can easily scratch it with your finger. Or hard as a diamond. One thing I could do, if I take my quartz sample, which is here, and I scratch calcite with it. So calcite I think is like a 2 or a 3. I guess we could look it up. Quartz is usually a 7. So calcite, want to know how hard it is. Quartz is a hardness of 7 on the scale. Calcite is a 3. So if I know these two different hardnesses, I should know that if I take my quartz, which is this guy here, and my calcite, and I scratch them I should know that my quartz will scratch my calcite. So I can see that it scratched it there. Didn't scratch this one. So I know that my quartz, since it's scratched my calcite, is harder than it. It's just a relative scale. So that's what we literally do. We take one mineral and we scratch it with another one. Run along, kiddos. Daddy's recording a video. Cool, but you shouldn't be up now anyway, because it's still early. Okay, so that's all that they do with the malt hardness scale. They take one mineral, try to scratch another one. Whichever one scratches the mineral is the harder one. Whichever one gets scratched is the softer one. Okay, so you can use your fingernail to do this. If I had talc, if I could find it quickly, you could scratch that with your fingernail. Your fingernail is a hardness of 2.5, I think. A nail is a hardness of 4 or 5. Glass, since it's quartz, is a hardness of 7. So you can use common everyday things in your house to figure out the rough hardness of things in your yard, minerals, that kind of stuff. Okay, so the mineral that scratches is the harder one. Specific gravity is the density of the mineral compared to water. So how you do it on like a scale is they have like a specific gravity mode. You take the weight of the mineral hanging from a little string. You literally tie it on a string and you have it hanging from this little hook and you weigh it in the air. Then you have it still on that string and you put a beaker of water underneath of it and it gets you a different weight, because if you've ever noticed that when you're in a swimming pool, it's a lot easier to lift people up because they're a little bit more buoyant. The water is helping kind of get rid of some of their weight, the force of gravity. So the weight of a mineral in water is less than the weight in the air. And you use this little formula to figure out the specific gravity, which can help you ID them. Then there's a bunch of different special properties. We've got magnetic. We've got ones that react with acid, meaning they'll bubble when you put acid on them. Fluorescent, so if you put them under UV light, they give off different hues or crazy colors. Or forms double images, which I can't even show you that one. Calcite is one that will form a double image, but the one I have here is not clear enough to even see through. So when you look at, like if I put this calcite on a piece of paper and there was a letter written under it, you would see 2 of them. I wonder if I can Google it, since I can't show you, but I can show you a couple of the others other than fluorescence, because I don't have a black light here. Image. I read an article once that they were trying to use calcite to kind of make an invisibility cloak of some sort. But if you put a clear piece of calcite on any kind of writing on a piece of paper, it makes this double image. So it actually kind of bends the light in a way that creates 2 different paths for the light. Okay. So if I pause this briefly, I think I can do that. Nope. Let's go on an adventure then. I've got my calcite, I've got magnetite. I haven't tried these yet, but we'll see. Magnetite should lift up some metal of some sort. Right. Hey, let's get the vinegar now. I tried it with vinegar actually, but maybe it's strong enough. But calcite, since it's got calcium in it, will bubble when you put acid on it. I always use hydrochloric acid, which I don't have here. That's disappointing. There are very, 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 very few bubbles with vinegar. It must not be strong enough. Not even close enough for me to be able to show you. I don't know. Usually when I've used magnetite, it's barely strong enough to lift up the paper clip. There's some here. Safety pin will possibly work. Let's give that a shot. And this one might not be super magnetic anymore either, so that's disappointing. Didn't work. Woohoo. So let's go to our good old YouTube. Suppose I could have just done it this way to begin with. Outside and yep, they are. Okay, so that only happens on elements that react with acid or minerals that react with acid, the compounds that are in them. If we take a look at magnetite, that's a magnet, not magnetite. Well, what I get if I just magnetite. That looks like a magnet too. That looks like a magnet. Okay, there. Yeah, I don't know what they're gonna do here. Nope, no magnetite there either. Well, well. Okay. The only other thing that I briefly wanted to talk about was just some of this stuff on this ID chart, because you're going to use this for one of your worksheets on Friday. No, you won't have school on Friday, so never mind. It'll be next week. So it just lists all the hardness. It has these ones over here that are cleavage versus fracture. That means if you hit them with a hammer, they're just going to break apart if they fracture into chunks. They don't really break on certain lines. If you hit them and they break on really even planes, or they break into cubes or things like that, it's called cleavage. It just breaks or cleaves on a very even plane. It describes colors. This is where you're going to get some of the special properties or densities. Specific gravity is very similar to density. Different colors of streaks, different feels for them. Uses, you'll find out what they're used for. So magnetite is an iron ore. It's used for steel. Galena is used for batteries. The lead inside of a car battery is mined from galena. Food additive for halite melts ice because it's NaCl. It's table salt. All sorts of different stuff in here. It does have a key for the elements down here in case you don't have a periodic table with you or don't remember. But one of your worksheets just has you kind of find different elements, tell me about them, or I ask you for an element that's got a certain hardness and you have to tell me what it is. I don't think I've posted this to Classroom yet, but I will the day that we actually work on this worksheet. Otherwise, that should be everything for me.